So this is where we left off last time. We figured out, let's back up, from the very beginning, right? We ran into this problem. We had a D2 ion. We realized that electron-electron repulsion was something that we had to take into account to accurately predict the UV spectrum, which was showing 3 peaks, when your intuition would kind of think without electron-electron repulsion, you'd only get 1 peak because you have a T2G to EG gap in octahedral. Okay. So obviously it's much more complicated than that. We went through and figured out all the different microstates to figure out how to group these microstates, the 45 different microstates, into different energy terms, which we call electronic states. From that, we figured out the ground state was triplet F using Hund's rules. Once we figured out the ground state was triplet F using Hund's rules, then we knew that there's only one spin allowed transition under a free ion. This was a free ion. We're not in octahedral symmetry yet. And that was to go to a triplet P excited state. Now what we did in the last video was descend into symmetry into octahedral, which is what our molecule that we're studying, this vanadium hexaaqua complex, was. Okay, and so we figured out the energetics for these terms when we go into octahedral symmetry. So the triplet F splits into a triplet T1G, a triplet T2G, and a triplet A2G. Where we got those term symbols from, the symmetry of those term symbols from, we don't go over in this class, but we were able to understand that's just a naming thing, it's not really that important. What we were able to understand was the electronic configurations that gave rise to those terms, okay, and what the energies of those terms would be as a function of electron-electron repulsion, this Rockoff parameter B, and as a function of delta O. And the triplet P just transformed as triplet T1G. And so it didn't split any further when we went to octahedral, but it caused this added confusion where we had two things cause triplet T1G called triplet T1Gs, one that came from the triplet P and one that came from the triplet F. So to start out, now what we're going to do is we're making a Walsh type diagram. And this is from spherical symmetry to octahedral symmetry, specifically for transition metal complexes, for d orbitals. Okay, this specific type of Walsh diagram has a special name called Tanabe Sugano diagrams, because it was designed and discovered or come up with by those two scientists. Okay, and so what we're going to do to make these correlation diagrams, these Tanabe Sugano diagrams, is we are going to first assume an extremely weak field. So if we, that means a weak splitting between T2G and EG, the octahedral splitting. So this would be like you have a very, very weak ligand, but you still have an octahedral symmetry. That essentially makes all these delta O terms go away. And so we start with our spherical ion, then we split, but a very weak split. EG and T2G are barely separated, but we do have the ligands. We have the 6 ligands, so we're octahedral. And so we know how the triplet F is going to split. It's going to split into those 3 terms we just talked about. The triplet P splits into terms. I put in parentheses triplet P for the triplet T1G and triplet F for this triplet T1G to tell you, hey, this triplet T1G came from the triplet P. Hey, this triplet T1G came from the triplet F, to distinguish between the two. All right, that's when you have a weak field. Now you're going to go to strong field. This is when you're going to have a meaningful delta O. Delta O is going to be much bigger than this Rockoff parameter of 15B. Okay, so when we do that, now we have actual splitting and we have to think about delta O. So we include these delta O terms. And what's going to happen? Well, this triplet T1G, triplet F state is not going to change in energy because it's 0 delta O. But these are 1 delta O, 2 delta O, and 1 delta O. How is that going to work? Triplet T1G, triplet F, didn't change in energy, just go straight across. Now you have the triplet triplet T2G. That I'm drawing with a line. Why do I draw that line? Because there's a 1 delta O. So as I get, the slope is delta O here. As I get to stronger and stronger field, I'm going up. Triplet T1G from the triplet P, that also had a 1 delta O term. So that line's going to go up. And I didn't have enough room, but the slope of this line and this line should be the same. I just didn't have enough room for the slide, okay? Then we have the triplet A2G. This had 2 electrons in the EG, and so it had 2 delta O term. So that slope is going to be twice of these slopes, which are supposed to be equal, okay? So that's what it's going to look like. And what we're going to do is we're going to plot this in terms of energy. These units are going to be in terms of B, okay, the Rock-R parameter. These energy units are going to be in terms of delta O. I wrote it here, delta O divided by B. What does that mean? That means energy units in terms of delta O. So it means how many times bigger is delta O than B. Same thing here would be E divided by B, okay? And how many times bigger is E than B? So if you have an E divided by B of 15, that's saying 15B. If you have a delta O divided by B of 10, that's saying 10 times delta O. Energy is 10 times delta O. This diagram is the full-blown analysis. And finally, we can explain why the vanadium hexaaqua 3+ complex has 3 absorption peaks. Why? Ground state is triplet T1G. Spin allowed states, one is going to the triplet T2G. Second one, going to the triplet T1G. Third one, going to the triplet A2G. So all of that worked, and now we can explain why D2. And by analogy, why D2 has 3 peaks in the UV-Vis spectrum. And by analogy, we can do any d electron configuration, although the work will be very, very complicated. What we just did is we derived the D2 Tanabe Sugano diagram. Okay, and so if you look in the handout on Web Campus, this is what the D2 Tanabe Sugano diagram looks like. There's a few differences, okay? One is it contains all the energy states. So Tanabe and Sugano diagram also calculate the singlet states. We don't really care about those, you know, because we know the ground state is triplet T1G, and so we here just only focus on the triplet state. But it also has these silent states, we can call them these singlet states. The other thing that you'll notice is that the G symbols were dropped, right? We don't have triplet T1G at the bottom. Imagine a line here straight at the bottom, that's the ground state. We don't have triplet T1G, it just says triplet T1. And it turns out that because octahedral and tetrahedral complexes are related, what we'll learn in future videos is that you can use these Tanabe Sugano diagrams to interpret tetrahedral complexes as well. It's really powerful. And so we keep the diagram generic and we drop the G's. Okay? And so you can see, you know, how these terms split. F, we had an F term that split into A2G, T1G, and T2G, and we had a P term that split into T1G. This is just for your information. You can derive these, but we're not going to do it in this course. So this is just the states in an octahedral field as things split. And so in the next video, now that we finally, you know, we're able to solve the main problem at hand, we're just going to learn how to interpret Tanabe Sugano diagrams and how to understand the relationships between them, how to use them for octahedral and how to use them for tetrahedral complexes. So all of this was just basically deriving a Tanabe Sugano diagram. You didn't know that that's what we're doing at first, but that's what we did.